Yes, there is a minimum distance requirement from a 34.5 kV to 277/480 volt silicone fluid power transformer installed outdoors to an elevated metal water tank. The minimum distance is 10 feet. This requirement exists primarily to mitigate the risks associated with electromagnetic fields, or EMF, generated by the transformer. These fields can induce currents in nearby conductive objects, such as a metal water tank, potentially leading to a hazardous situation. The 10-foot distance is intended to minimize the exposure of the water tank to the electromagnetic field emanating from the transformer. Several factors contribute to the need for this clearance, including the voltage level of the transformer, the type of fluid used for cooling and insulation, and the presence of nearby conductive structures. Firstly, the voltage level of the transformer plays a significant role. A 34.5 kV system operates at a high voltage, creating a stronger electromagnetic field compared to lower voltage systems. Secondly, the silicone fluid used in the transformer, while offering excellent insulation properties, does not eliminate the generation of electromagnetic fields. Thirdly, the elevated metal water tank acts as a large conductive object that can readily couple with the electromagnetic field, leading to induced currents. The induced currents in the metal water tank can manifest in several ways. One potential issue is the creation of circulating currents within the tank structure. These currents can lead to heating of the metal, potentially causing thermal stress and, in extreme cases, structural damage. Another concern is the possibility of electrical arcing. If the induced currents find a path to ground through a high-resistance connection, it can result in electrical arcing, which poses a fire hazard and can damage equipment. Furthermore, the presence of induced currents can interfere with the operation of sensitive electronic equipment located near the water tank. The electromagnetic interference, or EMI, can disrupt the functioning of control systems, communication devices, and other electronic components. To ensure safety and prevent potential hazards, it is crucial to maintain the minimum 10-foot clearance between the transformer and the metal water tank. This distance provides adequate separation to minimize the electromagnetic field exposure and reduce the risk of induced currents. In addition to the minimum distance requirement, other mitigation measures can be implemented to further reduce the impact of electromagnetic fields. One approach is to use shielding materials around the transformer to contain the electromagnetic field. Another option is to install grounding systems to provide a low-resistance path for induced currents to flow to ground. Regular inspections and maintenance of the transformer and surrounding equipment are also essential to identify and address any potential issues. These inspections should include checking for signs of overheating, corrosion, or other damage that could compromise the integrity of the system. Moreover, it is important to ensure that all electrical connections are properly tightened and that grounding systems are functioning effectively. Compliance with relevant electrical codes and standards is also paramount. These codes provide specific requirements for the installation and operation of electrical equipment, including transformers, to ensure safety and prevent hazards. It is essential to consult with qualified electrical engineers and contractors to ensure that all applicable codes and standards are met. In summary, the 10-foot minimum distance requirement between a 34.5 kV to 277/480 volt silicone fluid power transformer and an elevated metal water tank is a crucial safety measure to mitigate the risks associated with electromagnetic fields. By maintaining this clearance, the exposure of the water tank to the electromagnetic field is minimized, reducing the potential for induced currents, heating, arcing, and interference with electronic equipment. Regular inspections, maintenance, and compliance with relevant electrical codes and standards are also essential to ensure the safe and reliable operation of the electrical system. The 10-foot clearance is not an arbitrary number, it is based on engineering calculations and industry best practices to ensure a safe working environment. Factors considered in determining this distance include the transformer's voltage, its kVA rating, the type of cooling fluid, and the presence of other metallic structures nearby. The higher the voltage and kVA rating, the stronger the electromagnetic field produced, and therefore the greater the required clearance. Silicone fluid transformers, while offering advantages in terms of fire resistance and environmental impact, still generate electromagnetic fields that need to be managed. The presence of a large, grounded metal object like a water tank within close proximity to the transformer can create a pathway for induced currents. These currents can flow through the tank and back to the transformer, creating a closed loop. The magnitude of the induced current depends on several factors, including the strength of the electromagnetic field, the size and shape of the water tank, and the conductivity of the metal. If the induced current is high enough, it can cause several problems. Firstly, it can lead to resistive heating of the water tank. The flow of current through the metal generates heat, which can raise the temperature of the tank and its contents. This can be a concern if the water is used for cooling or other temperature-sensitive applications. Secondly, the induced current can create magnetic fields around the water tank. These magnetic fields can interfere with the operation of nearby equipment such as sensors, control systems, and communication devices. Thirdly, the induced current can create a potential difference between different points on the water tank. This potential difference can be a shock hazard to personnel who come into contact with the tank. To mitigate these risks, the 10-foot clearance is required. This distance provides sufficient separation to reduce the strength of the electromagnetic field at the location of the water tank, thereby minimizing the induced current. In addition to the clearance, other mitigation measures can be taken to further reduce the risk of induced currents. Firstly, the transformer can be shielded with a grounded metal enclosure. This enclosure will intercept the electromagnetic field and divert it to ground, preventing it from reaching the water tank. Secondly, the water tank can be grounded to the electrical system. This will provide a low impedance path for induced currents to flow to ground, minimizing the potential difference on the tank. Thirdly, surge arresters can be installed on the transformer and the water tank. These devices will protect against voltage surges caused by lightning or switching events, which can exacerbate the induced current problem. Fourthly, the routing of cables and conductors near the transformer and the water tank should be carefully planned to minimize electromagnetic interference. Cables should be shielded and grounded, and they should be kept as far away from the transformer and the water tank as possible. Fifthly, regular inspections and maintenance should be performed to ensure that the transformer, the water tank, and the grounding system are in good working order. Any signs of corrosion, damage, or loose connections should be promptly addressed. In addition to the above technical considerations, it is also important to comply with all applicable electrical codes and standards. The National Electrical Code, or NEC, provides detailed requirements for the installation and operation of electrical equipment, including transformers. These requirements are designed to ensure the safety of personnel and property. It is essential to consult with a qualified electrical engineer or contractor to ensure that the installation meets all applicable requirements. The specific requirements may vary depending on the location of the installation and the type of equipment being used. For example, in some areas there may be additional requirements for seismic protection or environmental protection. In summary, maintaining a minimum 10-foot clearance between a 34.5 kV to 277/480 volt silicone fluid power transformer and an elevated metal water tank is essential for safety. This clearance reduces the strength of the electromagnetic field at the location of the water tank, minimizing the risk of induced currents, heating, shock hazards, and interference with equipment. Other mitigation measures such as shielding, grounding, and surge protection can also be taken to further reduce the risk. It is important to comply with all applicable electrical codes and standards and to consult with a qualified electrical engineer or contractor to ensure a safe and reliable installation. It is also worth noting that the minimum distance requirement may vary depending on the specific circumstances of the installation. Factors such as the size and shape of the water tank, the type of metal used, and the presence of other nearby equipment may affect the required clearance. In some cases, a greater clearance may be necessary to ensure adequate safety. Therefore, it is always best to consult with a qualified electrical engineer to determine the appropriate clearance for a particular installation. Furthermore, it is important to consider the potential for future changes in the installation. For example, If the water tank is enlarged or if new equipment is installed nearby, it may be necessary to re-evaluate the clearance requirements. Regular inspections and maintenance should be performed to ensure that the clearance remains adequate over time. A 10-foot minimum clearance is a guideline, not a rigid rule, and the overall goal is to minimize the potential for hazardous induced currents in the metal water tank. This can be achieved through a combination of distance shielding, grounding, and careful design of the electrical system. The specific combination of measures will depend on the particular circumstances of the installation. A thorough engineering analysis should be performed to determine the most effective and cost-effective approach. This analysis should consider all relevant factors, including the voltage and kVA rating of the transformer, the size and shape of the water tank, the type of metal used, the presence of other nearby equipment, and the applicable electrical codes and standards. The analysis should also consider the potential for future changes in the installation. The results of the analysis should be documented in a written report, which should be kept on file for future reference. The report should include a detailed description of the installation, the analysis performed, the results of the analysis, and the recommended mitigation measures. The report should be reviewed and updated periodically to ensure that it remains accurate and up to date. Finally, it is important to remember that safety is always the top priority. If there is any doubt about the safety of an electrical installation, it is always best to err on the side of caution and consult with a qualified electrical engineer. A small investment in safety can prevent a serious accident or injury. And remember, this information should not be considered a substitute for consulting a qualified professional.